Welcome to Bot Thoughts by AmtocSoft. I'm Alex, and joining me is Sam. Today we're pulling back the curtain on something that sounds almost paradoxical. The largest language models in the world, GPT-4, Mixtral, Claude, aren't actually using all of their parameters on every single token you generate. Most of those parameters are idle most of the time. Sam, this is the mixture of experts architecture, and I think it's one of the most misunderstood ideas in AI. What's actually happening here?
Core intuition is specialization. Imagine instead of one generalist who answers every question, you have 8 specialists, one for math, one for coding, one for medical questions, one for creative writing, and so on. When a question comes in, a fast router looks at it and says, "This is a math problem, route it to experts 3 and 5. Only those 2 experts do the work. The other 6 sit idle. You get the combined knowledge of 8 specialists, but you only pay the compute cost of 2. That's what a mixture of experts model does at the level of transformer layers. The experts are feed-forward network submodules inside each transformer block. The router is a small neural network, literally a few hundred parameters, that decides which experts to activate for each token. A typical MOE model has 8 experts per layer and activates 2 per token. So you might have a model with 141 billion total parameters, but only about 12 to 14 billion are active at any given moment.
This concept has been around since the 90s. Why is it suddenly everywhere in large language models right now?
2 developments converged. First, the hardware. Running a 141 billion parameter model is only practical when those 141 billion parameters are distributed across many GPUs and the routing is fast enough to not become a bottleneck. That became tractable at scale in the last few years. Second, training MOE models at the quality level of dense models was historically difficult. The load balancing problem is subtle. If all tokens always get routed to the same 2 experts, those experts overspecialize and the others become dead weight. You need auxiliary loss functions during training that encourage uniform routing across experts, making sure every expert gets a roughly equal share of tokens. Getting that balance right without hurting model quality was an open research problem for a long time. Mixtral 8x7b, released by Mistral in late 2023, was the breakthrough that proved you could train a high-quality open-source MOE at scale. Suddenly, every major lab had MOE roadmaps.
Is GPT-4 a mixture of experts model? I've heard speculation, but OpenAI has never confirmed it.
OpenAI has not officially confirmed the architecture of GPT-4. What has leaked and been widely reported, with OpenAI neither confirming nor denying, is that GPT-4 is an MOE model with approximately 8 experts and around 220 billion total parameters, activating roughly 55 billion per forward pass. The math is consistent with its observed inference cost relative to its benchmark performance. What we do know from official sources is that Mixtral 8x7b from Mistral is MOE and performs comparably to GPT-3.5 on many benchmarks, and Mixtral 8x22b activates 39 billion out of 141 billion parameters and is competitive with GPT-4 on several coding and reasoning benchmarks. Claude's architecture is not disclosed by Anthropic. DeepSeek v3, one of the most capable open models in early 2026, is explicitly MOE. 671 billion total parameters with 37 billion active per token.
So the big pitch of MOE is that inference is cheaper. How much cheaper are we actually talking about?
The arithmetic is clean. Mixtral 8x7b has the compute cost of a 12-14 billion parameter dense model at inference time, despite having 47 billion total parameters, the full capacity of a model much larger. Benchmarks show it outperforms LLM 270b on most tasks while running about 5 times faster and using about a third of the VRAM during inference. That's the value proposition. You're paying inference costs proportional to the active parameters, not the total parameters. The trade-off is on the memory side. You have to load all 47 billion parameters into VRAM even though you're only computing with 14 billion at a time. So MOE is memory-intensive but compute-efficient. That's why MOE models are primarily deployed on multi-GPU setups. You need enough VRAM to hold all experts in memory, but you're only doing forward-pass math on the active fraction.
How does the router actually decide which experts to activate? Is it deterministic?
The router is a small learned linear layer plus a softmax. It takes the token's hidden state, a vector of numbers, and outputs a probability score for each expert. The top K experts, usually 2, are selected based on those scores. So yes, it's deterministic given a fixed model weight. The same token in the same context will always route to the same experts, but it's not rule-based in any human-readable way. The routing decisions emerge from training. Researchers who have probed these routers find loose specializations. Some experts activate more often on code, others on numbers, others on specific languages. But the specialization is probabilistic and distributed, not crisp. One expert might handle 80% of French text, but still activates occasionally on English. There's active research into making routing more interpretable, but it's not a solved problem.
Can you fine-tune a mixture of experts model? And does fine-tuning break the routing?
You can fine-tune MOE models and the routing doesn't catastrophically break, but there are specific challenges. If you fine-tune on a narrow domain, just medical text, just Python code, you risk collapsing the routing. The model sees a highly homogeneous distribution and starts routing everything to the same 1 or 2 experts, undermining the specialization that makes MOE efficient. The mitigation is to include diversity in your fine-tuning data even if it's outside your primary domain. Mix in general instruction data at about a 10 to 20% ratio. The other challenge is parameter efficiency. MOE models are larger in total parameters, which makes full fine-tuning expensive even if inference is cheap. Low-RA, low-rank adaptation is the standard approach. There's active work on MOE-specific low-RA variants that apply adapters selectively to the experts rather than uniformly. But most practitioners today use standard low-RA on top of MOE models without major issues.
DeepSeek v3 came up earlier. That was a massive moment in early 2026, a model that matched GPT-4 class performance from a relatively small team. What made their MOE design notable?
DeepSeek v3 introduced 2 architectural innovations on top of standard MOE first, a concept they call multi-head latent attention, an attention mechanism that's specifically designed to reduce the KV cache memory footprint during inference, which is a major cost driver for long context models. Second, a fine-grained expert architecture. Instead of 8 large experts, they use 256 smaller experts per layer, but still only activate 8 per token. This much finer granularity gives the router more combinatorial flexibility. The set of 8 active experts from 256 possibilities gives an astronomically large number of distinct routing patterns. The hypothesis is that this fine-grained routing captures more nuanced specialization without requiring more compute. The training cost they reported was remarkable: 2.78 million GPU hours of H800 compute for a model that rivals GPT-4 class performance. That's roughly $6 million at commercial cloud rates, far less than what equivalent dense models cost to train.
For a developer who wants to run a mixture of experts model locally or in their own infrastructure, what should they know?
2 practical realities. First, VRAM requirements. Mixtral 8x7B at 4-bit quantization fits on a single 48 GB GPU like an A6000 or L40S, or across 2 consumer 3090s with 24 GB each. At full precision, BF16, you need about 90 GB of VRAM, so 2 A100s or a single H100. Mixtral 8x22B at 4-bit needs about 65 GB. Full precision pushes 260 GB. DeepSeek v3 is not practically self-hostable for most teams. 671 billion parameters is data center territory. Second, inference frameworks. Llama supports Mixtral 8x7B and several other open MOE models natively. VLLM has MOE-aware scheduling and is the standard for production serving. LM Deploy from Shanghai AI Lab has good MOE support and strong benchmarks on Mixtral. The key thing with MOE serving is to load the full model into VRAM before accepting requests. You don't want to swap experts in and out from CPU, which would kill your latency advantage.
Where is MOE heading? Is this the architecture for the next generation of frontier models?
The trend is clearly toward MOE at the frontier. The compute efficiency argument is too strong to ignore. You get the model capacity of a very large, dense model at the inference cost of a much smaller one. The open questions are at the edges. Routing interpretability. Can we understand and control which experts handle which types of content? Expert collapse under fine-tuning. How do you maintain routing diversity when adapting to specific domains? And the memory wall, as models scale, carrying all expert parameters in memory becomes the bottleneck. Some researchers are experimenting with dynamic expert offloading, where rarely used experts live on CPU and are paged in only when needed. That's slower but allows running models that exceed GPU memory. The next 3 to 5 years of frontier model architecture will almost certainly be MOE, with ongoing innovation in routing mechanisms, expert granularity, and memory management.
3 concrete takeaways for developers listening to this.
First, when evaluating models, look at active parameter count, not total parameter count. A 47 billion parameter Mixtral model runs like a 12 billion parameter dense model at inference time. Comparing total parameter counts across dense and MOE models is an apples to oranges comparison. Second, if you're choosing between self-hosting Mixtral 8x7B versus a dense 13B model on the same hardware, Mixtral will likely outperform the dense model while using similar compute, but will need more VRAM to hold all experts. Make sure your GPU setup can carry the full model before you benchmark. Third, if you're fine-tuning a MOE model for a specific task, add diversity to your training set to prevent routing collapse. Monitor which experts are being activated during fine-tuning using Lang-Smith or weights and biases. If you see routing concentration to 1 or 2 experts, add more general data. The full technical breakdown, including how to run Mixtral locally and benchmark it against dense alternatives, is in our blog post at amtocsoft.blogspot.com.
Sam, this has been fantastic. One of those topics where the more you understand the architecture, the better your model selection decisions get. For everyone listening, the blog post goes deep on DeepSeek v3's architecture innovations and has a comparison table of MOE versus dense models across benchmarks, VRAM requirements, and inference cost. Link in the description. Subscribe on YouTube or wherever you get your podcasts, and support the show at buymecoffee.com/AmtocSoft. I'm Alex, Sam's been Sam, and this is Bot Thoughts. We'll see you in the next one.